3-core cables and also solve some of the numerical problems. Okay, upon completion of this lecture, you can deduce the equation for calculating the capacitance for a 3-core belted cable, and also you can solve numerical problems which are related to grading of cables as well as capacitance of 3-core belted cables. Okay, right. So now see the capacitance of 3-core belted cable. Okay, 3-core belted cables. So now in overhead transmission line also we were calculated the capacitance. So but when you compare overhead transmission line with underground cable, the capacitance is more important in underground cables. So why? Because in underground cables the conductors, conductors, or you can also say that cores, those cores are very near to each other. So in case of overhead transmission line, it is far away when compared to the underground cables. And also there is a effect of earth on the conductor also. So here the capacitance in case of underground cable is more important than the capacitance in overhead transmission lines, right? So now let us take one 3-core belted cable. 3-core belted cable. In this cable you are having 3 cores. Now when you supply the power through these 3 cores, so now because of the voltage difference between the any 2 cores, you will be having electrostatic forces here. In a similar manner, between the conductor and earth also, you have the potential difference. So because of that potential difference, there exists a electrostatic forces or electrostatic flux, right? So these electrostatic forces are between the conductor, between 2 conductors, and conductor to earth will be represented with capacitance. Okay, so actually in this figure 1, you are having the 3 cores. So between core to core, you are having the electrostatic flux, and at the same time between one conductor and earth. Earth in the sense here, sheath here, ma'am. So this outer sheath is connected to earth here. Okay, so now between this conductor and this sheath, which is connected to earth, you will be having electrostatic field. Okay, so because of these electrostatic fields, you will get 2 capacitances. So one capacitance is between two conductors or 2 cores. So here you will get one capacitance, and between one conductor and earth, you will also be having some capacitance. Okay, like that between any 2 conductors, you are having the capacitance, and from conductor to earth, you will be having capacitance. Okay, so the capacitance which is between 2 conductors is called the core to core capacitance. Okay, or this will be represented with CC. Okay, and the capacitance between one conductor to earth is represented as earth capacitance, so which is CE. Okay, so now the equivalent circuit for this cable is represented in equation figure 2. Okay, here we are having core to core capacitance between any 2 conductors, and there is a capacitance between one conductor to earth. So this is earth here. Okay, so now from this again you develop the equivalent circuit. So now if you observe this is one delta connection. See here, let us call the conductors will be A, B, C. So there are 3 conductors. These are represented with A, B, C. So let us call these are the conductors. Now between any 2 conductors, you have the capacitance CC. So if you take all the 3 capacitances, so then they will be like a delta. Okay. So now if you observe the one conductor to earth capacitance, which is CE. Okay, this CE is connected from A to earth. So this is from B to earth, and this is from CE to earth. So instead of assuming this round shaped earth, so we will take one single this one single point. So let us call it as earth here. Okay, so now between conductor A and earth you have one CE, and between B and earth you will be having another CE, and C and earth another will be having another capacitance. Okay, so this is the equivalent circuit for this 3-core belted cable. So mute your audio, ma'am. Okay. So this is the equivalent circuit for 3-core belted cable, in which you are having one delta connected cable, 3 delta connected capacitances. These capacitances we see, and 3 star connected capacitances. These are the star connected capacitances, which are CE. Okay. So now you take the delta connected capacitances. So this CC. First you take delta connected capacitances. Now you convert this delta connected capacitance into star. Right, you know the star, delta to star conversion. Okay. So when there are resistors and inductors, you will be having one formula to calculate, and for capacitor reverse. Okay. So when you are converting the capacitances which are connected in delta to star, so then the equivalent capacitance in star will be equal to 3 times of this. Okay. Actually CC plus CC into CC by CC. Okay, CC will get cancelled, so that equivalent capacitance will be 3 CC. Okay. So all the phases. So in star connection, all the capacitances will be 3C value only. Okay, why? Because in delta connection also, all sides will be having same capacitance. Okay, so when you convert the capacitances which are connected in delta to star, so then that star capacitances will be 3 times the delta connected capacitances. Okay, suppose if these are in resistances, so if the resistances are connected in star and all the resistances are same value, so now this delta connected resistances are converted into star connected resistances. So then this star connected resistance value will be equal to delta connected resistance value by 3. R by 3, R by 3, R by 3 will get. Okay. So suppose if there are inductors also, you will get, if there are delta connected inductors, so then in star there will be L by 3, L by 3, L by 3, like that you get. So but for capacitance it is reverse. Okay. So if you are having 3 capacitances of same value in delta connection, then that value will be equal to sum of all these. 3 times CC you will get, right? I think you know these. So this is about the converting this star connected capacitance into star, from delta to star. Again, you are already having another delta, star connected capacitances, which are CE, right? So you are having already CE between all the 3 phases. Okay, here you are having A, B, C. So here you are having CC, CE, and CE. So now this delta connection is also converted into star. Okay, so now this star is superimposed on this star. So then here this CE equivalent and this CE will become parallel. Okay, this neutral and this neutral will be the same. Okay, now these two will be superimposed. That means those two are connected. So this is also connected to A and this is also connected to A, and these two are the same neutrals. So CE will be parallel to CC. Okay, C equivalent will be parallel to CE, and this C equivalent also parallel to this CE, and this C equivalent will be parallel to this CE. Okay, now the complete equivalent circuit will become like this. So this is the complete equivalent of circuit for this diagram. Okay, so now capacitances are connected in parallel. So now the total capacitance will be represented with Cn. So that Cn will be equal to Ce plus 3 Cc. Okay, so Ce equivalent here is nothing but 3 Cc. Okay, when capacitances are connected in parallel, the total capacitance will be sum of these two, Ce plus Ce equivalent. So Ce plus, in place of Ce equivalent you can write 3 Cc. Okay, so then Cn will be Ce plus 3 Cc. In all the phases you will get the same value. Okay, so now here Cn is the capacitance between one conductor to your earth or neutral. So that is Cn is called the phase capacitance, per phase value. Okay, Cn is the per phase capacitance of a 3-core belted cable. Okay, this is how you can calculate the capacitances. Okay, so Cn is Ce plus C equivalent, so which is equal to Ce plus in place of C equivalent, you can write phases. So this is the per phase capacitance for a 3-core belted cable. Now, if you know the values of this Ce and Cc, you can get the per phase capacitance of your 3-core belted cable. Okay. So now, how you can calculate this Ce and Cc? So generally, these Ce and Cc will be maybe empirical values for 3-core belted cable, or you can also measure by using some measuring equipment. Okay. So by using some measuring equipment, you can measure the Ce and Cc values, or you can choose the empirical value, already determined values for the Ce and Cc, so that you will get the per phase value of capacitance for a belted cable, right? Now, if the V phase is the per phase voltage, so then the charging current IC can be represented with IC is equal to V phase by capacitive reactance XC. Okay. So this is the XC value, capacitive reactance. So that capacitive reactance is represented with 1 by omega C. Okay. Omega C, see here what you are taking here, Cn. So then this value will become, so again here omega is 2 pi f. So 2 pi f into Cn into V phase you will get 2 pi f into Cn. V phase is the your charging current, and Cn value is Ce plus 3Cc. Okay, as I said before, this Ce and Cc are the empirical values, so already determined values for a belted cable, depending upon the operating voltage and size of the cable. Or if you want to calculate, then by using some measuring equipment, you can also determine the Ce and Cc values. Okay, so now let us see how you can calculate by measurements the values of Ce and Cc. Right? So by measurement, how you can calculate the Ce and Cc, let us see. So now first you calculate this for calculating Ce. So for calculating the Ce, you have to bunch the all the 3 cores. Okay. So if you observe this diagram, second diagram, you are having 3 cores, right? Now these 3 cores are bunched together. So that means you have to consider only one core. All the 3 cores are bunched in this like this. So that means you will not be having this CC here. So all the 3 cores are bunched together, so that there is a one single core, and you have to measure the capacitance between this bunched core and the sheath. So which is the sheath which is connected to earth. So which is this. So you are already having these 3 Cs. Okay, this is Ce, this is Ce. Okay, so when you bunch all the 3 cores together, so then these eliminates the Cc value, right? So we will be having only Ce. Okay, so and now you have to measure your capacitance by connecting your measuring terminals between your bunched core and this earth. So now if you connect a measuring meter here, this measuring meter will give you the value of the capacitance. So let us call it as C1. C1 is the value measured by this measuring meter. Now this C1 will be equal to. So now from this diagram, what you can say? So you are having one conductor, and between conductor and earth you will be having one Ce, and from the same conductor and earth again you will be having another Ce. Okay, so this is earth. And between this conductor and you will have another Ce. So total you are having 3 Cs. This is Ce, this is Ce, and this is Ce. So you are having total 3 Cs which are connected in parallel. So between the bunched core and your earth. So now the total equivalent capacitance when 3 cores are 3 capacitance are connected in parallel will be sum of all these. So which is 3 Ce. Okay. So now from this you can calculate the Ce value as C1 by 3. Okay. right? So for measuring this CE value, you have to bunch all the three cores together, and between the bunched core and your earth, which is sheath, you have to connect your measuring meter. Now this measuring meter will show some value, right? Let us call that value to be C1. So C1 will be the measuring value. Now this measuring value will be equal to total equivalent capacitance of these three. Okay, so that means total equivalent capacitance will be 3 CE. So C1 will become equal to 3 CE. So now from this expression you can calculate the CE as C1 by 3. Okay, so this C1 is the capacitance which is measured by your measuring meter. Okay, right, now you got the CE. So next, how you can calculate for CC, right? For determine for calculating the C, here you have in the second measurement you have to bunch two cores. Two cores are bunched together with the sheath, and capacitance is measured between them and the third core. Okay, so here you have to bunch two cores with the sheath. So you have to bunch three cores with the sheath, and capacitance will be measured between the bunched core and the third core. Okay, what it means here is, here you are having three cores here. Let it be 1, 2, 3. Right? In the second measurement, so any two cores you have to bunch with the sheath. So this is your sheath. So this will be connected to this directly. So that means here you will get it. And this is also two cores, right? Two cores are bunched to the end. So that means this is also connected here. This is also connected. So this value and this value will be gets cancelled. So what? So now between this bunched core, that means which is connected to here, and the third core, you have to measure the capacitance. Okay. See here, you are having third core. This is CE. Now you are going to bunch your two cores with your sheath. Okay. That means the sheath is connected directly to your conductor. Now here you will be having CE. Between these also you are having CE. So between these two you are not having any capacitance. This CC and these two Cs, these will be eliminated here. Okay, so now these two conductors are bunched together with the sheath. So because of this, this is CE, this is CE, and this is CC. So these will be eliminated. Okay, so now you have to measure the capacitances between these bunched cores. That means between this bunched cores, and between this and the third core, this. Here you have to connect your measuring meter. Okay, so now the measuring meter value you have to consider it as C2. Okay, so C2 is your measuring value. Now for this, if you draw the equivalent circuit, so what will be the your C2? Okay, generally this is connected, this sheath will be connected to earth. Okay, so now you consider your third core here, bunched core, sorry, third core, bunched core is nothing but your earth. So now between this earth and third core, so here you are having third core, between third core and earth you are having, so 1 cc. Okay, this is 1 cc between third core to this, and between this to earth also, this is also another, between third core and earth again we are having another cc. Third core and again sheath. The sheath is nothing but other CE. Okay, so that means again you are having two CCs and one CE connected in parallel. So now that total equivalent capacitance will be this CE plus 2 CC. So this is the value of the C2. Okay, so measuring value C2 will be equal to this is CE plus 2 CC. Okay, so from this you can calculate your CC. Okay, CC is equal to C2 minus CE by 2. So like that you can calculate your CC, right? Okay, ma'am. So this C2 is equal to 2 times CC plus CE. Okay. So from this expression, you can calculate the value of CC. So that CC is equal to C2 minus CE, sorry, CE this one, by 2. Okay. Now you got the value of CC. Right. So to calculate this CC value, you must and should do this measurement. Okay. So first you have to calculate CE, then you have to calculate C2. So then the CC value will be C2 minus CE by 2. This is how you can calculate the value of CC. Right. So these are the two measurements for calculating CE and CC. So now after calculating this CE and CC values, so you can calculate the per phase capacitance Cn value by using this formula. Cn is equal to Ce plus 3Cc. Okay. So else you are having one direct measurement for calculating this Cn value. So let us see what is the direct measurement. Right. So now you can also calculate the value of Cn directly. So now for calculating Cn value directly, you have to do another test. So in this test, you have to find the capacitance between two cores, with the third core connected to the earth. Okay. So you have to measure the capacitance between two cores with the third core connected to earth. So that means you are having, actually you are having three cores. Those out of those three cores, two core between two you consider two cores, and the third core will be connected to earth. Earth in the sense this sheet here. Okay. So now you will be here. You will be having core to core capacitance. Here you will be having core to core capacitance, and here also you will be having core to core capacitance. And between here you are having C. Core and earth you will be having C. Okay. So this is the test. In this test, you can calculate the value of Cn directly now. Instead of calculating Ce and Cc, you can calculate the Cn value directly by using one test. So in this test, you have to measure the capacitance between two cores. That means you have to connect your measuring meter between these two cores. Okay, you have to connect the measuring meter between two cores, and you have to calculate the capacitance between those two cores with the third core is connected to earth. So that means this third core will be connected to earth here. Okay. Now from this after measuring the value, so let us call that value to be C3. Okay. Now C3 value is your direct, sorry, C3, let us call it as C3. So then for this circuit you develop the equivalent value. Okay. So now here you are having two cores on reactor. See here, let us assume there are two cores, so between which you are having this CC, so this capacitance. Okay. So then this is your earth. So now between this core and earth you are having CE. So from this core to earth you are having one CE value, and between this core and earth you are having another CE. So this is another CE. Okay. That means this value, this and this is represented. Now what are the other things? This is also taken between this core and earth. Again you will have CC, on this core and earth you are having CC. So that means here you are having CC. Here also you are having CC. Okay. Now you observe here. So these are connected in parallel and these are connected in parallel. So then the total capacitance will be. So now you will get like this. Here we will be having CC and here you will be having CE plus CC. CE plus CC. Here also you will be having CE plus CC. Okay. So now your equivalent to what you have to, you are connecting your measuring meter between these two. Okay. So now when you are connecting your measuring meter between these two cores, so now this CC will be in parallel with combination of these two. Okay. Right. So that value, these two, that means CC will be in parallel with series combination of these two, CE plus CC and CE plus CC. When the capacitors are connected, same capacitors are connected in series. Suppose C and C both are connected in series, the equivalent value will be C by 2. Okay, so that means CC will be in parallel with CE plus CC by 2. So now the equivalent value for parallel combination will be sum CC plus CE by 2 plus CC by 2. So this is the value of C3 here. Okay. So is it okay, ma? Are you understood this value? C3 is CC plus CE by 2 on CC by 2. This value. C3 is equal to CC plus CC by 2 and CE plus CE by 2. Okay. So now from this expression you can write, you can take 1 by 2 as common. Then you will get the C3 as 1 by 2 into CE plus 3CC. Okay, you sum this. Okay, so take 2 as common. Then this will be 2CC plus CC plus CE. So that value will be 3CC plus CE by 2. 3CC plus CE by 2. Now what is this CE plus 3CC? From here this expression CE plus 3CC. So this CE plus 3CC is nothing but your CN value. So you substitute that value here. In place of CE plus 3CC, you can substitute CN value. Now that CN value will be equal to 2 times your C3. Okay. So CN value is equal to 2 times your 2 times of C3. Okay. This is how you can calculate the per phase capacitance directly. Okay. Right. So any doubt here, ma'am? So this is about the capacitance of calculation for a three-phase belted cable. See here. Up to this, you are not having any doubts, I think. So the per phase capacitance CN value will be CE plus 3CC. Okay. So from this expression, to get the per phase value of CN, you have to calculate. You have to know the value of CE as well as CC. Now, the CE and CC values may be empirical values, which may be determined from the scientist, and they will give that directly for a cable for the some size and operating voltage. So, or if you are having your cable, then you can also in the laboratory you can also calculate it by some measurements. Okay, so you have to do 2 measurements. Okay, so in one measurement you will get the CE value, and in another measurement you will get CC value. Okay, so in the first measurement, what you have to do? In the first measurement, you have to bunch all the 3 cores. All the 3 cores will be bunched together, and you have to measure the capacitance between that bunched core and sheath. Sheath is nothing but sheath is connected to earth. Okay, so you have to bunch all the 3 cores, and you measure the capacitance between bunched core and sheath. So then that value you call it as C1. Okay, so now this C1 value will be known from the measurement. Okay, so now this C1 will be equal to from the equivalent circuit you will get 3 CE. Okay, how you will get this 3 CE I was explained. Okay, now from this equation CE is equal to C1 by 3. Now in the second measurement you have to bunch two cores with your sheath. Okay, two cores are bunched with the sheath, and capacitance will be measured between this bunched core and the third core. So we are having three cores. Out of three cores, two cores will be connected to sheath, and you have to measure the capacitance between the third core and the sheath. Okay, so that you call it as C2. Okay, that C2 value now you will get from the measurement. Now from equivalent circuit you will get this C2 will be equal to 2Cc plus Ce. So from this expression Cc is equal to C2 minus Ce by 2. Okay, so this is how you can get the values of Ce and Cc. Now once if you get Ce and Cc, you use this formula to get the per phase capacitance. Per phase capacitance Cn is equal to Ce plus Cc. Okay, so this is one method. So now in another method, instead of calculating Ce and Cc, you can directly get the value of Cn. So Cn, which is the per phase capacitance. Okay, so to get this Cn value directly, you have to do another test. So in that test, you have to you have to measure the capacitance between the two cores with the third core connected to the sheath, okay, or earth. You have to measure the capacitance between two cores and the third core will be connected to here. Then that capacitance value will be, let us call it as C3. Now this C3 value will become equal to Cc plus Cc by 2 plus Ce by 2. How you get this? We will explain that, right? So now from this you will get 1 by 2 Ce plus 3 Cc. So now this Ce plus 3 Cc, from here this value is Cn. So this will become 1 by 2 Cn. So that means C3 is equal to 1 by 2 Cn. So from this equation, Cn is equal to 2 times the C3. Okay, C3 is the measured value, and this expression is the our calculated expression. So which is same as the C3 value. So this C3 value, known value. So on Cn you can calculate. Okay, by using this expression. Okay, right now. So let us see a few problems related to this capacitance. Okay. First here, so the capacitances of a three-phase belted cable are 12.6 microfarad between three cores bunched together under the lead sheet. Okay, that means if three cores are bunched together under lead sheet, so then if you measure the capacitance between the three core bunched together and lead sheet, that value will be called as C1, first measurement. Okay, so that first C1 measurement is 12.6 microfarad here. Okay, and they were also given 7.4 microfarad between one core and other two cores connected to the sheath. Okay, so that means C2 value is also given in the problem. Find the charging current drawn by the cable when it is connected to 66 kV and 50 Hz supply. Okay, so in the given problem, the measurement values are given here now. Okay, so these two measurements they were done, and the values of C1 and C2 are given. Okay, the C1 value is 12.6 microfarad and C2 value is 7.4 microfarad, and the voltage, operating voltage, is 66 kilovolts. Okay, so now if you can, this is the line-to-line voltage. If you want the per phase value, so V phase is equal to 66 into 10 cube by root 3. So that value is 38105 volts, and frequency also given as 50 Hz. So these are the given values. Now you have to calculate the charging current. Okay, so charging current IC is equal to 2 pi f V phase Cn or Ce plus 3Cc. Okay, so now you use this equation. IC is equal to 2 pi f V phase Cn. Okay, in this expression frequency is known and V phase is known. First you have to calculate Cn before getting IC. How you can calculate this Cn? Okay, So the C1 value is already given. So that C1 value from the first measurement is equal to 3 times CE. Okay, C1 is equal to 3 times CE. So C1 is equal to 3 times CE. So from this expression, CE value will be equal to C1 by 3. So C1 value is 12.6 by 3, which is equal to 4.2 microfarad. Okay. So then C2 value is also given, and that C2 value is 2 cc plus CE. Okay. C2 is equal to 2 cc plus CE. Now here in this expression, C2 value is given, which is 7.4 microfarad, and CE value we were calculated, which is 4.2 microfarad. Then you will get the value of CC. That CC is equal to C2 minus CE by 2. Okay, that value is 1.6 microfarad. So now you got the value of CE as well as CC. Now the core to neutral capacitance CN value will be equal to CE plus 3cc. Okay. So now you substitute the value of CE and CC in this expression. You will get the capacitance between your core and neutral, which is 9 microfarad. So the charging current will be IC is equal to 2 pi f V phase into CN, and the all values, frequency, V phase and CN values are known. So you can calculate the charging current by simply substituting them. Then you will get the value of 107.74 amperes. Okay, this is the charging current flowing through belted cable. So this charging current is also per phase value, right? Because here you are taking the all values, V phase and CN are the per phase values. So let us see another problem. So the capacitance per kilometer of a 3-phase belted cable is 0.18 microfarad between two cores with the third core connected to the seat. Calculate the kVA taken by the 20 kilometer long cable when it is connected to 3-phase 50 Hz 3300 volts supply. Okay. So now here, if you observe the problem, 0.18 is the capacitance value. So between two cores with the third core connected to the seat. That means, so they were given the value of C3. Okay, C3 is the measurement value. So if you measure the capacitance between two cores with the third core connected to the seat, that C3 value is directly given as 0.18 microfarad. So this 0.18 microfarad is for 1 kilometer. Okay, this is per kilometer. So, but your cable is 20 kilometer long. So for 20 kilometer long, the total capacitance value of C3 will be 0.18 into 20 kilometers you have to take. So this value, C3 value will be 3.6 microfarad per the total length of the cable. Okay. So now what is this C3? C3 from the third means C3 is equal to Cn by 2. Okay. So from this expression, Cn value is equal to 2C3. Okay. Cn is equal to 2C3. So C3 here is 3.6 microfarad. So you will get the per phase capacitance Cn value as 7.2 microfarad. Okay. So once you get the per phase capacitance, you can calculate the charging current. Charging current IC is equal to 2 pi f V phase into Cn. Now frequency is given 50 Hz and V phase is the per phase voltage. Actually here 3300 kilovolts is the this is line voltage. So you convert into phase voltage by dividing it √3, so that you will get 1905 as your voltage, per phase voltage. Now that per phase voltage is 1904 and Cn value is 7.2 microfarad. Okay, then you will get the charging current as 4.3 amperes. So now after calculating charging current, they were also called to calculate the kVA, kilovolt ampere. So kVA taken by the cable. So kVA, volt ampere is nothing but voltage into current. Okay. So in terms of kilovolt amperes you have to consider. So volt ampere rating for the 3-core cable will be 3 times V phase into IC. Okay, 3 times V phase into IC. So now you know the value of V phase and also IC. So then if you calculate the kVA, you are getting 24.57 kilovolt ampere. Okay. So this is how you can calculate the charging current flowing through your cable and the kVA taken by the cable. So let us see another problem. So this is the same as the problem number 2. So you do as a exercise. Okay, I was given only the problem, so you do it at home. So this is similar to this problem number 2. So once read the problem. So the capacitance per kilometer of three-phase belted cable is 0.3 microfarad between two cores with the third core connected to the lead sheath. That means C3 value per kilometer is given, which is 0.3 microfarad. So 0.3 microfarad is the capacitance between two cores with the third core connected to the lead sheath. So which is C3 value. Okay, now calculate the charging current taken by 5 kilometers of this cable. This is for 1 kilometer. C3 value given is for 1 kilometer. So for getting 5 kilometers, you have to multiply this value with 5. So 5 into 0.3 is the C3 value actually. Okay. So then you have to calculate the charging current. And the cable is connected to three phase, 50 Hz, 11 kV supply. So 11 kV is the line to line voltage, you convert into the phase voltage, and the charging current will be determined from this expression. Okay. So once you do this problem at your home. Okay, which is similar to the second problem only. Right now. So this is about the capacitance of the core cables. Now, if you are having any doubts, you can ask me. So we have not done the problems which are related to your grading of cables. Okay, we have done only the problems up to the capacitance of three core belted cable till now. So till now, if you are having any doubts, you ask me.
క్లాస్ ఉందా ఎప్పుడు 12
అయిపోయింది 10 minutes ఉంది.
నాకుంది క్లాస్ 12 to 1 దిగిందా నడుస్తుంది
If no doubts, we will proceed to the problems which are related to the grading of cables. Okay. So yesterday we discussed about the grading of cables, capacitance grading and intensity grading. So this grading will be done to achieve a uniform dielectric stress in the cable, okay, or to minimize the dielectric stress throughout the length of the cable. Or you can also say that to increase the operating voltage for a particular cable, you can use the grading. Okay, so grading will be capacitance grading and intersheath grading. In capacitance grading, you will use the different dielectric materials which are having different relative permittivity. Okay, you can use layers of dielectric permittivities, their layers of dielectric materials in capacitance grading. So in such a manner that the value of epsilon, this permittivity value will be in the order of decreasing order from conductor to earth. So that means epsilon 1 will be greater than epsilon 2 and epsilon 2 will be greater than epsilon 3. Like that, you have to arrange your dielectric materials in such a way that the material which is having highest permittivity will be placed nearer to the conductor. So then the another layer will be connected on the first layer. So like that, in the decreasing order of permittivity, you have to place the dielectric materials. Okay. Then the dielectric stress will be same at the all the layers. And in case of intersheath grading, so you will use the same dielectric material. Okay, only one dielectric material you will use. But in intersheath grading, you will use intersheaths. Okay, so generally you are having one conductor and earthed sheath. So between this conductor and earthed sheath, again you will use the some metallic sheath in between. Okay, so those metallic sheath may be one or two or more. Okay, any number of metallic sheath may be placed between your conductor and a earthed sheath. Okay, the sheath which is connected to earth, which is called the earthed sheath. Okay, so because of connecting these metallic sheaths between conductor and earthed sheath, your dielectric stress will be minimized, or you can get the uniform dielectric stress. Okay, this we were previously discussed in the previous lecture. So we didn't solve any problem on this grading of cables. Okay, I think what is the time now? We are having 5 minutes of time. So let us see one problem on dielectrics, and the remaining problems we will discuss in the next class. See the problem number 4, which is related to the grading of cables. Right. So read the problem. A single core lead sheathed cable is graded by using 3 dielectrics of relative permittivity 5, 4 and 3 respectively. So the conductor diameter is 2 centimeter and overall diameter is 8 centimeters. If the 3 dielectrics are working at same maximum stress of 40 kilovolts per centimeter, find the safe working voltage of the cable. Okay, and also what will be the safe working voltage for a ungraded cable, assuming that same conductor and overall diameter and maximum dielectric stress. Okay, first you have to consider a single core cable, right? And that single core cable is graded by using 3 dielectric materials. So these 3 dielectric materials will be having relative permittivity 5, 4 and 3 respectively. Okay, that means first layer or first dielectric material will be having 5, next 4, next 3. Suppose if these values are not given in decreasing order, you have to consider that your first layer will be the layer which is having highest permittivity. So sometimes instead of giving 5, 4, 3, so they may even give the values like this, 3, 6, 2 like this. So now if you observe here, your this value will be greater than this, and this value will be, so that means the highest value will become the your epsilon 1. The first layer will be your highest permittivity value. So next it will be epsilon 2, next highest value will be epsilon 3, like that. We have to place the all the dielectric materials in such a manner that the permittivities will be in decreasing order. Okay, first layer which is near to the conductor will have high permittivity. So if you consider this case, 6 will be the epsilon 1 and epsilon 2 will be 3 and epsilon 3 will be 2. Okay, So now for this given problem, they were given the permittivity values in decreasing order only. So there is no problem. Okay. So suppose if they were given in uh, different manner, that means minimum value is first given, maximum value is next given, then you have to take care of that. Okay. You have to arrange your dielectric materials in such a manner that the permittivities will be in decreasing order from conductor to your earthed sheath. Okay. So now here in the given problem, as they were already given in the decreasing order, so this epsilon value, epsilon 1 will be 5, and epsilon 2 will be 4, and epsilon 3 will be 3. Okay, and they were also given the conductor diameter and core diameter both are same. So that means this value, this diameter, conductor diameter, small d value is given, which is equal to 2 centimeters. And overall diameter of the cable, in the sense from here, earthed sheath to here, this overall diameter is given as 8 centimeter. Now let us call that overall diameter as capital D, which is equal to 8 centimeters. Okay, epsilon 1, epsilon 2, epsilon 3 values are given, and small d and capital D values are given. And in the problem, they said that the three dielectrics are working at the same maximum stress. Okay, dielectric stress, maximum dielectric stress will be same for all the three dielectrics. Right? So when all the three dielectrics are working at the same maximum stress, now you have the condition, this condition. Epsilon 1 into D is equal to epsilon 2 into D1 is equal to epsilon 3 into D2. So this we got while discussing the capacitance gradient. Okay. So epsilon 1 D, epsilon 2 D1, epsilon 3 D2. So right. So now D1 and D2 here is the diameter of your. So this is first layer D1, and second layer it is D2. And sheath it will be, it is capital D, overall diameter. And for only conductor it is small d. Okay. So now you know the value of D and you know the value of epsilon 1, which is epsilon 1 is 5 and D value is 2. So 5 into 2 you will get 10. And epsilon 2, you don't know the value of D1 but you know the value of epsilon 2. So 4 into D1, which is equal to epsilon 3 value is 3, D2 is not known. Right, so this will become 3 into D2. So now if you take these two terms, then you will get the D1 value. D1 is equal to 10 by 4, which is 2.5 centimeters. And if you take these two, 3D2 is equal to 10, then your D2 value will be 3.34 centimeters. Okay. So now you will get, you got the values of D1 and D2 there also. So this is diameter of layer 1 and layer 2. So then the operating voltage. So when there is a same maximum stress in the cable, so then the potential difference between this core and earthed sheath, will be V is equal to G max by 2 into D ln D1 by D plus D1 ln D2 by D1 plus D2 ln capital D by D2. So this is the formula to calculate the potential difference and voltage, both are the same. Okay. To calculate the operating voltage, you have to use this expression. Now in this expression, G max value is this 40 kilovolts per centimeter. So that means 40 is the G max. And small d, small d1, d2, and capital D, all the values are known. So you simply substitute them. So then you will get the working voltage. Okay. So safe working voltage of the cable you will get. So the safe working voltage will be 81.8 kilovolts. So this is for graded cable. Suppose if you are not using grading of cables, so then the operating without grading will be equal to G max by 2 D ln capital D by D. So now here also all the values are known. So that value will be working voltage or operating voltage without grading is 55.44 kilovolts. Okay.